Okay, today we're going to talk about Hartree-Fock theory, what it is and how it works. Unfortunately, we won't really be able to get to the heart of Hartree-Fock theory till the next lecture, which will be Wednesday at this time in this room. And that's because it really takes a lot of notation to be able to write down the equations in a somewhat compact form. So it may take me quite a few minutes this morning just to get all the notation out there, but that's what I'll attempt to at least get done, and then we'll see how far we can get into the actual method. But let me remind you what it is we're doing, which is solving the Schrodinger equation for some molecule. And last time I wrote up the Hamiltonian, and I'll do that briefly again today just to kind of remind you. This time I'll go ahead and cheat, and I'll switch over to atomic units because it's faster to write down in atomic units. And that's because h bar becomes 1, mass of the electron becomes 1, 4 pi epsilon naught becomes 1. So lots of things become easier to write. So the molecular Hamiltonian is the kinetic energy of the nuclei. Last time and this time I'll call those capital A, capital B, etc. to mean nuclei. There. 1 over 2 times the mass of the nucleus times second derivative with respect to those nuclear coordinates. Same thing for the electrons, but that's easier to write in atomic units. And I'll use little I, little j, etc. to denote electrons. That's minus 1/2 del I squared, because the mass of the electron is 1 and h bar is 1 in atomic units. Okay, so I've got nuclear kinetic energy, electronic kinetic energy. What else do I have? I have potential energy. I have electron nuclear attraction. So I'm going to sum over all the nuclei, and I'm going to sum over all the electrons. And that's going to be the charge on the nucleus times E squared, but E in atomic units is 1. Divided by 4 pi epsilon naught goes to 1. Distance between electron I and nucleus A is RIA. I have electron-electron repulsion. That's positive. I'm summing over the unique pairs. I'll call that I greater than J. 1 over Rij. That's pretty darn easy in atomic units. And then finally, same thing for nuclear-nuclear repulsion. A greater than B, 1 over RAB. Okay, so that's all the terms in the Hamiltonian. And when we invoke the Born-Oppenheimer approximation, we're going to assume that the nuclei are fixed at some positions and just solve for the motions of the electrons. So that means I'm going to have a electronic Hamiltonian, which is going to basically neglect this term. Because if the nuclei are fixed, second derivative with respect to those is going to be 0. But then I'll just have the remaining bits. Now this guy, RAB, the sum of all the nuclear repulsions, that, strictly speaking, is a nuclear term. There's no electronic coordinates there, they're all nuclear. And so if I want to talk about solving the electronic Schrodinger equation, maybe I would take that out. But in practice, we normally go ahead and fold it into the electronic Schrodinger equation. And that's because if the nuclei are at fixed positions, that's just a constant, and the constant's just going to shift up the energies by some amount. It won't affect the wave function. And just practically speaking, electronic structure theorists go ahead and throw that in the electronic Schrodinger equation because it's easy to handle, even though strictly speaking it is a nuclear term. So if you do all this, you solve for the electronic Schrodinger equation, which is all of that minus this nuclear part. And the wave function is an explicit function of all the electronic coordinates, which I might call little r. And it also depends parametrically on the fixed nuclear coordinates. That gives me an electronic energy, which depends on the nuclear coordinates, times that wave function back. And I'll call this psi sub e because it's an electronic wave function. And then if I want to know what the nuclei are doing, I can then subsequently solve a nuclear Schrodinger equation where I take this nuclear kinetic energy, which I'll call Tn, plus this electronic energy now serves the role of the potential that the nuclei feel times a nuclear wave function equals the total energy times the nuclear wave function. Okay, that's all a bit of a reminder of some stuff I mentioned last week, but that's what we're going to do. Born-Oppenheimer approximation lets us solve the electronic Schrodinger equation. Once we have that, the electronic energies play the role of a potential energy that the nuclei feel, and then we can solve what the nuclei do. Then if we have the electronic wave function and the nuclear wave function, we kind of have everything. In principle, anything should be derivable from those quantities. This would only not work if you had very strong coupling between the nuclear and electronic degrees of freedom, which can occasionally happen. That's called a breakdown of the Born-Oppenheimer approximation. But it's somewhat rare that that happens unless you work in certain fields. For most run-of-the-mill problems, the Born-Oppenheimer approximation works great, and there is good decoupling between nuclear and electronic coordinates. Okay, so I'm going to solve the electronic Schrodinger equation, and what I need to do is now introduce some of this notation I've been talking about. Instead of writing all this, I'm going to write something even shorter than that. Now I'm going to refer to my notes to see what symbols I am using today. Yes. Okay. I'm going to introduce what I'm going to call a one-electron operator, little h of I, and this is going to be a so-called one-electron Hamiltonian for electron I. And what it's going to be is the nuclear kinetic energy of electron I, so the piece of this that corresponds to electron I, minus the attraction that that electron feels to all the nuclei. So sum over the nuclei, Z sub A over RIA. So the nucleus, the electron I has a kinetic energy, it has an attraction to all the nuclei. I have those two bits. That really describes electron I except for one other piece, the repulsion it feels from all the other electrons. That comes from here. I'm going to treat that one as a separate term because I want to lump the one electron bits together, so I'm going to call this the one electron Hamiltonian. The two electron bit, well, it's easy enough to write, but sometimes we write it Vij, which is really just 1 over Rij. So sometimes I'll use one, sometimes I'll use the other. And then with this notation, the electronic Hamiltonian becomes a sum over all the one electron terms, h sub I, plus a sum over all the unique pairs of these Vij's. And as I mentioned a second ago, it's traditional to go ahead and include the nuclear-nuclear repulsion, even though it's not really an electronic part. But anyway, VNN then is going to denote this sum here. And for fixed nuclear coordinates, it's just a constant. All right, any questions about where we are so far? If not, then let's roll on. All right, what am I going to do with this? How am I going to try to solve this? Well, next thing I need to do, I'm going to assume that the solution is a single Slater determinant. And I mentioned that last time. I'll write it up again quickly so we kind of remember what it looks like. We're going to talk a lot more about Slater determinants today. Okay, so I've got the Slater determinant. I'm going to call this, what do I want to call this? I'm going to introduce a shorthand for the Slater determinant as well. The Slater determinant is specified basically by what orbitals go into it. And the orbitals are columns, as I'll show in a second. And now I'm going to index them. I think I'll call them PQR, or something like that today. PQR. I'm going to put that in a ket symbol. I don't know if everybody's familiar with Dirac notation or not, but even if you're not, that's okay. We don't really need to worry about what it means right now. This symbol will denote the Slater determinant. there's a normalization factor, which is 1 over the square root of n factorial, where n is the number of electrons. Then each column denotes an orbital, and each row denotes an electron. So column 1 is going to be orbital p. I'm going to call the orbitals chi. And as I mentioned last time, x vector is going to denote a set of coordinates for electron 1. So x1, y1, z1, and the spin of electron 1. Maybe call it omega 1. So that's really 4 coordinates in one here in this vector x1. The next column is for the next orbital, which I'll call q. And so on and so forth up to orbital r. And it's all electron 1 in the first row. The second row is the same, except you switch to electron 2. x2, chi q of x2, chi r of x2, and so on and so forth. You get to the end. Chi p of xn, if you have n electrons, chi q of xn, and chi r of xn. Okay, so you can see why I want some kind of shorthand like this, because writing this more than once starts to get pretty tedious, and so we normally don't write it that way. But it does represent a determinant, and in fact, even the determinant's a shorthand, because you might remember if you have a 2 by 2 determinant, you can expand a determinant out. The 2 by 2 gives you multiplication going down the diagonal, subtract going up the other diagonal, you get 2 terms. If you had a 3 by 3, you actually get 1, 2, 3, 4, 5, 6 terms, which is 3 factorial. That's kind of why factorial shows up here. And in general, if you have a n by n determinant, you get n factorial terms out of it. So instead of writing n factorial terms, this is a lot shorter. But then instead of writing that, that's a lot shorter. Okay. I'll write those kets for these determinants. So this guy is going to be the solution to the electronic Schrodinger equation. Is it an exact solution? No, because the exact solution requires more than one Slater determinant. But to a pretty darn good approximation, one Slater determinant gives you a nice approximation to the electronic wave function. Much of the time. If you have transition metals or you're breaking bonds or you have diradicals, you really need to have at least 2 or sometimes 3 or 4 or 5 or 6 Slater determinants to even get a good approximation, even qualitatively sometimes. But if you've got a well-behaved molecule in its ground electronic state and you're not breaking bonds and it's not a transition metal, one of these is going to be pretty darn accurate. Okay, so then the question is how I get the orbitals, and that's what Hartree-Fock theory is going to do for me. And we're going to use the variational theorem. We're going to tweak the orbitals till we get the lowest energy possible, and that's what Hartree-Fock theory is going to do. So if I want to do that, how do I minimize the energy with respect to the orbital rotations? Well, I have to know what the energy is. So if I had a Slater determinant made out of these orbitals, looking like this with this normalization, and I wanted to get the energy of that, what would it be? Well, the energy we're going to assume, since we're doing variational approximations, I'm going to assume that the energy looks like a sort of a symmetric kind of quantity. I'll show what I mean by that. So we're going to assume we're going to work with an energy that looks like integral of psi, where this is going to be psi now. A Hartree-Fock wave. Maybe I should say psi Hartree-Fock so we kind of remember it's an approximate solution. Psi is that. So I take the Hartree-Fock wave function, take my electronic Hamiltonian. I'm just going to start writing H instead of electronic pretty soon, because in my job I only ever work with this one, pretty much. But it is the electronic Hamiltonian I'm talking about. If I integrate this over all space, then I get some Hartree-Fock energy. Maybe I'll call it E Hartree-Fock. And in Dirac notation, if you're familiar with that or if you're not, it looks like this. Where anything that is complex conjugate goes over here on the left, this is called the bra in Dirac notation because Dirac thought it was kind of a joke that you could have a bra, and this is called the ket, and then it spells bracket, and he thought that sounded cool. So anyway, this is called ket, that's called the bra. This is just the one that has a complex conjugate. And we don't need to write the integral because if you have an inner product like this, it implies that you're doing an integral over all space. So that's a definite integral, not an indefinite integral, so it actually values to a number, and energies should be numbers, and that's good. And in fact, because of the properties of the Hamiltonian and the symmetric nature of this, and the fact that the Hamiltonian is a Hermitian operator, turns out this number is guaranteed to be a real number, so it's not complex, and that's also good because energy should be real numbers. All right, so what I do is I take this and I plug it in here and there, take complex conjugates on the left side. I'm going to go ahead and assume I'm going to work with a real wave function psi in real orbitals. I don't have to make that assumption. In fact, probably the energy equation I'm about to write maybe doesn't necessarily make that assumption. But in practice, quantum chemists don't like writing codes with complex numbers. So in reality, if you were going to literally do this on a computer, the program would almost invariably assume that these are real and everything works out to be real. All right, so how in the world do I plug this in here and there and actually get some number out of this? This looks insanely complicated. Well, you could brute force it. If you had, say it was just a 2x2 case, you could do it. If it was a 2x2 determinant, well, you can expand a 2x2 determinant and you get a couple terms, and you could throw that in here and here, or there and there. And it would be really messy algebra, but after some patience and effort, you would write down this big long expression and you'd have the result for the energy as a function of those orbitals. But it turns out it's a little easier than all that. Even if I have a 10 by 10 or 100 by 100 or 1,000 by 1,000, it simplifies a lot because if I think back to the nature of H, which I just erased, H, remember, it has 1 electron terms and 2 electron terms. That means the Hamiltonian only deals with at most 2 electrons at once, like the electron-electron repulsion term. That's the 2 electron term. There's no terms in the Hamiltonian that involve 3 electrons or 4 electrons or 5 electrons. That winds up being very helpful to us. Because of that, many, many, many of the terms that come out when you expand this determinant all drop out to 0 or 1, which is great. It would take too long to actually prove that to you, so I'm not going to do that, but maybe I can kind of convince you. Suppose you multiply this out. When you do, you get a product of orbitals. You get, like, say I go down this diagonal, that's going to be one of the terms, and there's many other terms. Chi p of x1 times chi q of x2 times some other stuff down here times chi r of xn. So I get a product of orbitals. There's n of those orbitals in the product if I have n electrons. And each orbital has a different electron in it, either x1 or x2 or whatever. All right, so I get a product of n orbitals. Suppose I have such a product here on the left and another product on the right. The different terms in the determinant will give me plus and minus a bunch of other possible products. I'm not worried about that right now. Each of those products, though, has n orbitals multiplied by each other here, and n orbitals multiplied by each other here. If this is a 2-electron operator, it can do something to 2 of those electrons. Let's say electron 1 and electron 2 for the sake of simplicity. But then if it's affecting electron 1 and electron 2, it has no power left to do anything to electron 3, 4, 5, 6, whatever. And that's good because if I have such a product here, and I have electron 3, say, in orbital chi, I don't know, q, let's say t, I don't want to interfere with some other letter I've used. Suppose I've got chi t here of x3. And then some stuff here, but electron 3 is not affected. Then on the other side, suppose I've got chi, I don't know, s of x3. Well, other stuff may happen with respect to electron 1 and electron 2, but with respect to electron 3, I've got electron 3 in orbital t, or orbital s, these orbitals, we choose them to be orthonormal. And because of that, that term will go to 0 unless s equals t. And if s was t, then it would go to 1. So all these guys, some of you may have taken a class where they denoted that as Kronecker delta. You get lots and lots and lots of Kronecker deltas for the any pair of electrons that aren't the two that are present inside a piece of this 2-electron Hamiltonian. So most of the terms, well, all the terms go to 0, 1, except for bits that involve at most 2 electrons. And then those are the bits that remain. And if you're interested to see the details of how this works, the book by Szabo and Osland, Modern Quantum Chemistry, actually derives these so-called Slater rules that I'm about to give. All right, but hopefully that gives you a flavor for why they simplify. So, given that, it turns out that if I have a Slater determinant and I try to get its matrix element like this, I only get 1 in the 2 electron terms. For this particular one, I get, refer to my notes to make sure I don't switch notations on myself unnecessarily. Yep, there we go. All right, this guy winds up being a sum over I. That quantity, which I'll define in a second, plus this quantity, which I will also define in a second. These are sums over electrons again. Okay, that's the Hartree-Fock energy in terms of 1-electron quantities and 2-electron quantities. But what are these quantities? Okay, well, hopefully this little h reminds you of the little h I had a minute ago, the 1-electron operator, and that's exactly what it is. This is the same thing. Maybe I should put a hat on it, I guess I did before. This is just a matrix element of the 1-electron operator for orbital I. And to write that out explicitly, so you have a little bit more of a clue what that is, it's this. Let me switch from Dirac notation to integral notation in case that makes some of you happier. I've got an electron in orbital I. It's a function of its 3 spatial coordinates and its spin coordinates, which I'll call x1 vector. I have this H operator here. And I have this guy again. Like that. Okay, so that's all it is. It's just this operator, and I put some orbital on the right and the left and integrate over all space. How do I do this integral? Well, that's the subject of a whole other lecture or series of lectures. But in principle, you could do it, right? It might be hard, but you could do it. Okay, so in the end, I get a number, right? It's a definite integral, so I get a number out of that. Now, and what is this number physically? This reflects basically the kinetic energy of electron 1 in orbital I, because that was a part of H, remember? What was the other part? Its attraction to all the nuclei. That's in there too. And the reason I have to do all this integration and stuff is, well, because it's quantum mechanics, and the electron isn't just sitting at some point in space. It's smeared out, and it has different probabilities of being at different locations. And that's what the chi star chi is kind of giving me. That's the probability that electron 1 in orbital I is at location x1 at any given moment in time. And then I multiply those probabilities by what it would do at that location with respect to its kinetic energy and its attraction to all the nuclei. Okay, so that's that. This bit gets the remaining physical part, which is what? The electron-electron repulsion. And these are the so-called 2-electron integral terms. And this, I'm going to make myself some more space, I think. I don't think we'll need this again. Let me go up here just in case I want that in a second. Okay, so this other one, let me write it generically. I should have written this generically too. This is correct, but you could also have a more general form of this orbital is different than that one. It doesn't happen in Hartree Fock, but it could happen somewhere else. So I could, if I wanted to, I could call that P and that Q, P and Q. That would be fine too. Let me go ahead and write this one in a generic way. PQRS is, this is a so-called double bar integral. It's shorthand for PQRS minus PQSR. All right, well that doesn't help you much because you don't know what the other two things are. Okay, so let me define those. All right, so the other two guys, this is now called single bar integral, double bar. All right. PQRS is, well, it's one of these integrals. It's an integral over sets of coordinates for two electrons. I'll call it x1 and x2. Again, these are vectors, so they have 4 coordinates inside each of them. Chi, let's see, which one is this? P, x1, star, chi q of x1, no, chi q star of x2, 1 over the distance between the electrons, chi r of x1, chi s of x2. Okay, this is the so-called physicist notation or Dirac notation for the integrals, where the quantities that have complex conjugate are on the left in the bra, and the quantities that are not complex conjugate are on the right in the ket. And this is the electron repulsion between the two electrons. It's a little hard to decipher this physically, but we can do it. Let me go ahead and rearrange this in another form, since we are doing notation. This is the so-called physicist notation. There's another notation called the chemist notation, which is the same quantity, just written in a different way. The chemists tend to like to put electron 1 on the left and electron 2 on the right, because they think that's just easier to look at. So let me give you the chemist version of this. So we could do this. Now I'm going to put electron 1 on the left. P, x1, chi q of x1, chi r star of x2, chi s of x2. So now I have electron 1 here and electron 2 there. I could write things this way, but notice this is not identical to the thing above, because I swapped what letter was what, right? I had Q as complex conjugate of chi 2, now Q is not complex conjugate as chi 1. So this is not the same as that. But these are all kind of generic indices for the moment, so that's kind of okay. And I need a different symbol to denote this versus that, because you need to know what order they come in. So to use a different symbol, I'm going to use square brackets and write it like that. So that's going to be the chemist version. This is the physicist version. Now I can convert between the two. If this is defined, in fact, I will define it this way. If this is defined this way and this is defined that way, you can convert between one or the other, and we do that all the time in quantum chemistry. This guy, if I want to convert it, well, what's the same and what's different? P is the same, S is the same. What gets flip-flopped is the meaning of R and Q is changed. So this guy, to convert from one to the other, I just flip indices 2 and 3. This is the same as PRQS. Is that right? If I had an R here, that would be the same as that. Yeah. Okay, let me pause for a second since I've been dishing out some notation and say, does any of that make any sense, or any questions about one of these things, what any of these things are? People seem relatively happy. Okay, great. Let me see if I've told you everything you need to know about these things. No, not yet. Now, I've tried to write this in a nice generic form. I already mentioned, though, in reality, we don't like working with complex orbitals. So most of the time, in a real calculation, these orbitals will all be real. That means, well, whether I take this complex conjugate or not, it's irrelevant. If it's a real number, complex conjugate of a real number is just the real number back. So I don't have to do anything. So normally when we do these derivations, we try to be careful and proper at first, and we put all our complex conjugates where they go. And then later we say, all right, now I'm going to assume real orbitals, and then kind of simplify things. All right, now that's a kind of a relevant comment here because if I do assume real orbitals, I can get some extra little tricks I can play. Even if I don't, I've got some tricks I can play. Look at this guy first, this chi p star, chi q star product. Well, obviously, actually, let me be careful about what I say about that. I like to work with these guys instead. All right, which one of these do I want to tell you about? Okay, first thing, physicist notation. Does it matter which electron is electron 1 and which electron is electron 2? No, it's just a dummy index. Now, once you've picked one to be 1 and 1 to be the other, you need to be kind of consistent about what you're doing. But I'm integrating over x1, I'm integrating over x2. If I wanted to flip-flop which one was x1 and which one was x2, it would be exactly the same quantity, right? So in that sense, this thing must also be equal to what happens if I reverse electron 1 and 2. So what does that mean? It means I flip these two indices and I flip these two indices. So PQRS equals QP SR if I flip those two and those two, because that's just interchanging which one's electron 1 and electron 2, and that's irrelevant. I could do the same thing in chemist notation, but then that gets trickier in a way. No, easier in a way. Electron 1's now on the left, electron 2's on the right, so then in chemist notation, that means I just flip which one's the left and the right, so that's RSPQ. Okay, so I can do some tricks like that. The other thing I can do, if they're real orbitals, then if I look at this product, well, no, I want to look at this product. If they're real orbitals, if I look at P times Q, they're both x1, well, that's the same thing as Q times P, because it no longer matters which one's got a star if they're all real. So for real orbitals, I can then interchange P and Q, or by the same reasoning, R and S, and get exactly the same thing. And I could do an analogous thing up here in physicist notation. I could swap P with R, or Q with S. So there's a lot of swapping of indices you can do with these guys to show which ones are the same, which ones are different. And in my notes, I go through the full 8-fold permutational symmetry that these have if they're all real orbitals. And that's useful when you're doing derivations, because sometimes you'll derive one and then the other one, and then you need to realize, oh, these two are the same thing, and then you go ahead and add them up. Or sometimes you subtract them and you cancel. Maybe I'll briefly mention I've got these jotted down. I can write them down real quickly, but I don't. There it is. There they are. Yeah, so in terms of, I guess I will have to lose this line. In terms of chemist notation, I actually wind up, if you do all these tricks I said and put them all together, you get a whole bunch of permutations. IJKL winds up being the same thing as KLIJ. Mention that. Electron 1, electron 2 don't matter. But if they're real orbitals, then I can flip one of these. So that's the same as JIKL. But if I flip that one, I'm free to flip these two also. So that's the same thing as IJLK. But I could flip those at the same time. So that's the same thing as JILK. And then for each of these, I can flip left and right. Well, I already did that for that one. I haven't done that here yet. So that's the same thing as KLJI. And this is the same thing as LKIJ. And that's the same thing as LKJI. And how many do I have? 1, 2, 3, 4, 5, 6, 7, 8. Eightfold permutational symmetry. So, and you could do something analogous with this notation. All right, so I think that's enough notation. Now back to Hartree-Fock. Let me rewrite my Hartree-Fock energy expression. I need what I'm just erasing. Let me write that again. PQ double bar RS equals PQ single bar RS minus PQ single bar SR. Let me erase what's below that, I guess. To me, it's easier to understand the Hartree-Fock energy expression if you're in chemist notation, so that's the way I'm going to explain it to you. But it's valid either way, of course. So what did I say the Hartree-Fock energy expression was? Well, I said you sum up over all the 1 electron bits, and I hope you feel like you have a feeling for what those are. They're just kinetic energy and attraction to the nuclei. What's more interesting is these 2 electron bits. I did it as a double sum. 1/2 some orbital pairs of electrons. IJ. Did they do it that way or did they do it the other way? Yep, they did it that way. Let me decode this into chemist notation. This guy is equal to sum over I and J. What's IJ double bar IJ? I'm going to use this trick. It's IJ single bar minus IJJI. And now I'm going to convert that into chemist notation. How do you do that again? You swap indices 2 and 3. So that's the same thing as 1/2 sum over IJ. Bracket notation now. IIJJ minus IJJI. That's what it is in chemist notation. So, just went from double bar to single bar, then from single bar to chemist, you swap indices 2 and 3. You get that. But then I have to put it in brackets to denote that I've swapped notations. Now, the reason I like this is because at least part of this, you can get a physical understanding of what this is, which I'll see if I can squeeze in here or somewhere. We don't need this anymore now. So, what is this guy? IIJJ. In chemist notation, it's chi I star, electron 1, times, in chemist notation, electron 1 comes first, both times. Chi I times electron 1, times 1 over R, 1, 2, distance between electrons 1 and 2, chi J star of x2, chi J of x2. This guy actually has some physical meaning. Look at the left term. Chi I star chi I. What is that? If electron 1 is in orbital I, which it is for this purpose, then chi I star of x1, chi I of x1 is the probability that electron 1 in orbital I is located at position x1. Or more precisely, within some infinitesimal volume element centered around x1. All right, so that's the probability electron 1 in orbital I is at x1. But then by the same token, this is analogous. This is the probability that electron 2 in orbital J is at x2. All right, so there's some probability that electron 1 in orbital I is at this location, x1. And then there's some probability that x2 is where electron 2 is at in orbital J. if this electron were here, and if that electron were here, the distance between them would be R12, and then the repulsion between them would be 1 over R12, which is exactly what I wrote here. So what this is telling you is this is the Coulomb repulsion between two electrons, but it's a quantum mechanical version of a Coulomb repulsion because I don't know where the electrons are. I only know what their probabilities are. So if electron 1 was here and electron 2 was there, then the repulsion would be that. But do I know that they're there? No, they have some probability given by that times that. What if they're somewhere else? Well, they might be at some other location, x1, x2. That's why I integrate over all possible places either of them could be, and I integrate over all space. So over all space, electron 1 could be at position x1, electron 2 could be at position x2. That's the probability electron 1 is there if it's in orbital I. That's the probability electron 2 is in orbital is there if it's in orbital J. And then I just sum up all these probabilities times the Coulomb repulsion, and that gives you the overall quantum mechanical Coulomb repulsion between electron 1 in orbital I and electron 2 in orbital J. Does that make sense? I hope so, because the next term doesn't make sense. The next term is just like this. What is it? It's ijji. So the next term, what I do, that becomes a j, and that becomes an I. I can't make any nice hand-wavy argument like I just did. This doesn't have a good physical interpretation. The best we can say is it is close to something that does have a physical interpretation, but I've interchanged or exchanged two of the labels, these two. I've exchanged these two indices. And for that reason, this guy is called the exchange term. And it has its origin in the fact that we assumed a Slater determinant as the functional form for the Hartree-Fock wave function. That's really ultimately where it comes from. The fact that we need the wave function to change sign if I interchange two sets of electronic coordinates ultimately filters down and gives me that term. So it's really kind of a reflection of the anti-symmetry principle, or its special case, the Pauli exclusion principle, that term comes in. This term is just called the Coulomb term, and it makes a heck of a lot of sense. It's just the repulsion the two electrons feel, given the fact that they're in orbitals and they have different probabilities of being in different places in space. So that's your Hartree-Fock energy. It consists of kinetic energy for the electrons, the attraction of the electrons to the nuclei. Those are both folded up in that one electron term, a little h. And then there's a Coulomb term, which is often denoted J while I'm on notation. In Hartree-Fock theory, you notice the indices always come in pairs, right? There's two I's and two J's. Two I's and two J's. Because we quantum chemists really hate writing down more than we have to, if you haven't already picked up on this, we introduced yet another shorthand. It would call this guy Jij, and we call that guy Kij. And this is just easier to write. Because they always come in those pairs, at least in Hartree-Fock theory. Okay. So now we at least know what the Hartree-Fock energy expression is. It's a sum of the 1 electron bits for each electron. In fact, we also have a shorthand notation for this, by the way. Sometimes we'll call that little h II, where it just says, if it's an orbital I, it has that, and we sum over all the orbitals I. So you have 1 electron bit, 2 electron bits, 2 electron bits, Coulomb exchange. And there's your energy. And this I've written to be pretty generic. This equation should work no matter how many electrons you have, and you just sum up these things. One interesting factoid that might be useful if you ever play around with these equations, think about the special case I equals J. What happens there? Because I've written this as an unrestricted sum, the way I chose to do it right now. Well, if I equals J, I have I minus I. It cancels. That's good. So I don't have to worry about the case I equals J. If I wanted, I could rewrite this sum as just as the unique bits, I greater than J, Jij minus Kij, that would work out to be the same thing as this because the I equals J part cancels anyway. Now, it's an interesting little factoid that in density functional theory, this doesn't exactly happen that these exactly cancel for various reasons. And, well, those would still cancel, but there are other bits that go into the exchange. So you don't have an exact cancellation in density functional theory of exchange in Coulomb terms, which you should. So in a sense, in density functional theory, an electron can see itself, which is kind of bad. And that gives you something called the self-interaction error. And sometimes that can give you slightly weird results when you use DFT that you shouldn't get. Doesn't mean people won't use DFT because you get a lot of benefits from it. You know, there's always trade-offs. All right, any questions about any of that? All right, let's see.
There's actually another problem. If you have a delta function, so you're really deep into the periodic table, your Coulomb and your exchange are both infinity, so you have infinity minus infinity.
Yes, that's true too. Yes, there are lots of tricks that can come up with these equations. One has to watch out for. All right, well, now that I've got the energy, let me then see if I can at least get the stage started towards doing the derivation of the Hartree-Fock equations, which we will definitely not finish. But we can at least get it rolling, which would be a good thing. I think I'll leave Slater rules to Trent if he's going to do the CI lecture. I could talk about Slater's rules here, which are just what happens if I have two Slater determinants that are different. What are the matrix elements? But for Hartree-Fock, I only need the special case where it's the same matrix element, the same Slater determinant on either side. So I'll just run with that for now. But in general, it's also useful to know how to work out the matrix elements if you did have two different Slater determinants. And that is relevant for something called configuration interaction. All right, but now that I have an energy, which I'll probably have to erase to make room, but anyway, we've seen the energy, we can write it down in terms of these guys. Now we want to actually do Hartree-Fock. All right, so how am I going to do that? Well, we'll get it started on the equations, then we'll finish them next time. What I want to do is I want to tweak my orbitals, chi-i's, chi-j's, to get the minimum possible energy by the variational theorem. I mentioned that last time. So how do I do that? Well, I'm going to set up, starting to die on me, let me try something else. I'm going to set up a Lagrangian. Let's write it this way. It's going to depend on all the orbitals. So this is a function of all the orbitals. And it's going to be equal to the Hartree-Fock energy. Hartree-Fock energy also, of course, depends on the set of all the orbitals, right? Just saw that. Then I'm going to do this funny business where I'm going to subtract off these so-called undetermined multipliers. I'm going to call them epsilon ij. And I'm going to use those to enforce the constraint that the orbitals remain orthonormal. So what I want to happen is that this guy, which is just the overlap between orbital I and orbital j, so that's just that. If these are orthonormal orbitals, this should equal the Kronecker delta, which is just 1 if I equals j, or 0 if I is not equal to j. We want this to be true. To the extent that it's not true, we want to sort of force it to be true. So I'm going to kind of throw this in to my Lagrangian as a constraint, and this is kind of a useful trick when you're doing this kind of variational approach, as a way to kind of keep those orbitals orthonormal. Why do I care if the orbitals are orthonormal? Well, I mentioned a minute ago when we did our Slater's rules that all the terms besides the two electrons that are being operated on in the two-electron Hamiltonian go to 1 or 0 because the orbitals are orthonormal. I need that to stay true because otherwise my energy expression gets crazy complicated. So we want that to stay true, and we're just going to insist whatever it is we do when we vary chi-i and chi-j, we're going to vary them in such a way that they remain orthonormal, and then I can use the same energy expression. Okay. So instead of just sort of saying in words, u orbitals have to stay orthonormal, I'm kind of going to enforce it mathematically. All right. So I'm going to start with that, and then I'm going to minimize that instead of this, because if I just did a straight minimization of this, I might goof up my orbital orthonormalization. I'm going to minimize that with respect to the chi's. And I'm going to write down the so-called first variations, which basically means pretend you're going to kind of do a little tweak on chi-I or chi-j, and you're going to say, how much did capital L change? All right, so the change in this delta L, well, it's whatever the change is in the Hartree-Fock energy. We need to work out what that is. It'll have some change, which of course depends on the chi's. Minus, what happens if I do some tweak of chi-I or chi-j here? Well, subtract over ij, epsilon ij. Tweaking chi-I or chi-j doesn't change this. This is just defined as 0 or 1 if I equals j or not. So this doesn't change. Kind of like a constant here. These are constants here. But this will change because if this equals this, then if I tweak chi-I, it will, of course, change this result. So some little change in this changes this, and I need to reflect that here. And I'm going to call that, well, whatever the change is in this, which I'll work out in just a second. All right, so basically all I'm saying is, if you tweak chi-I, you can change that. We won't change that by definition. We will change that, but we won't change that. So now I need to know, well, what is the change in this and what is the change in that? The easy one to work out first is this, because that's the definition and it's pretty easy. Well, what happens if I do tweak chi-I to that? Let's assume that our tweaks have a certain form, which is this form. Let's say chi-I is tweaked a little bit and goes into chi-I plus delta chi-I. That'll be easy to track. Well, let me just kind of throw that in. What if I tweak chi-I this way? If I substitute that in here, well, I'll get the original integral plus some extra bit that involves this delta chi-I, right? I'll get, namely, delta chi-I here, plus chi-I delta chi-j. Because I could tweak either I or j. So whichever one, I get two terms. So that's okay. And I'm only interested in the change, so I'm not writing chi-I, chi-j again. That's where we started from. So I just want the difference. So the difference is either this tweak or that tweak. Now, what about the Hartree-Fock energy? That's probably a good place to stop, actually. The next thing I want to do is write down what the change in the Hartree-Fock energy is, which might take me more than a couple minutes, so that might be a good place to resume next time. We'll write down this tweak by writing down again what E is in terms of 1 and 2 electron integrals. We'll tweak each of those, kind of like this, but there's more of them. And then next time we'll kind of grind through the equations to see what all comes out of this, and then we'll collapse it back down into something we can work with, and then we'll have Hartree-Fock theory. And then if I have time, I'll say a little bit about, when we're done with the equations, about qualitatively how they behave, how they work, how I can converge them, things like that. Any final questions? Okay, if not, then for those who are interested in seeing the conclusion of this, I'll see you here Wednesday at 10.